Good morning and welcome back to the course of Microwave Engineering. In today's lecture, we will continue with the different types of material used for the construction of microwave integrated circuit. If you recall from our previous lecture, in the previous lecture we have gone through the major classification of microwave integrated circuit, and we have classified the microwave integrated circuit into two major categories, that is hybrid microwave integrated circuits and monolithic microwave integrated circuit. And we saw the typical construction of hybrid microwave integrated circuit and monolithic microwave integrated circuit, and we found out a variety of difference point between these two different types of integrated circuits used in microwave communication, right? And we have gone through the different construction principle of the hybrid microwave integrated circuit and monolithic microwave integrated circuit. Now in this particular lecture we will go ahead and today we will devote our time in order to study the different types of material used for the construction of microwave integrated circuit. Okay, so today we will discuss the microwave integrated circuit materials. So let us start with the microwave integrated circuits. Now here I will start and I would like to highlight this. This is the today's chapter, right? So actually the classification of microwave integrated circuit is categorized based on the different types of elements. Okay, so these elements are either used in the form of chip or they are fabricated directly onto the substrate of microwave integrated circuit. We already know from the definition of hybrid microwave integrated circuit that the discrete values of a components, including passive devices and active devices, they are directly taken from outside and they are bonded onto the substrate or they are soldered. Okay, on the case of monolithic microwave integrated circuit, we saw that the passive devices and the active elements are grown directly onto the substrate, right? So the three general types of a circuit which we normally encounter in the design of microwave integrated circuits are: the number one is the distributed transmission lines, okay, which are mainly acting as a conductor, which includes the use of microstrip transmission line, strip line, and coplanar transmission lines. Okay, so in the construction we may use the lumped circuit elements, which includes resistors, inductors, and capacitors. Okay, and finally in the integrated circuit we may be using the active elements, including our diodes and transistors. So those are treated as a solid state devices. Okay, so in the construction of microwave integrated circuit, the component wise the construction can consist of transmission lines, passive devices, and active devices, including diodes and transistor. Okay, so now we study what different types of materials are used for the construction of microwave integrated circuit. Okay, so based on the different types of elements that we want to construct over the integrated circuit, the materials used in microwave integrated circuit are classified into four major categories. Okay, so these categories are the substrate material, the conductor material, the dielectric material, and the resistive film. Okay, so these are the four different types of material we usually encounter in the construction of any microwave integrated circuit. The substrate material is not to be treated as a dielectric material. Now here whenever we say a substrate material, this substrate material indicates the base material over which the entire circuit construction of integrated circuit is made. Okay, so we have a rough definition that sometimes we used to call the substrate material as a dielectric material also. Okay, but this definition is not going to be true over here. Here the substrate material we treat as a separate, and they are used merely for the construction of the base material, okay, or they are used in order to form the platform on which the integrated circuit is built. We have the conductor material. The conductor material is mainly used for the purpose of transmission lines, right? And then the dielectric material. Okay, so the dielectric materials are required in order to form the different types of a layer. And if you want to make use of a capacitors also, then also we can make use of this dielectric material. And finally, the resistive films. Now the resistive films are going to provide us the values of different types of resistances, and even these resistive films can be utilized in order to fabricate the attenuator circuit over the integrated circuit, right? So each of these different types of material now we are going to explain with their desired properties. Remember that substrate materials, conductor material, dielectric material and resistive material, there are variety of different materials available, but we cannot make use of all these materials available for the fabrication of microwave integrated circuit, because these material they need to fulfill certain properties so that they can be incorporated in the construction of microwave integrated circuit. So let us start with the substrate material. Okay, so what are the substrate materials? These substrate materials are, they are used for the base for the fabrication of active devices. Okay, so this is the main use of substrate material. So the substrate materials are used in order to construct or in order to develop the active device, okay, in the fabrication. So the ideal substrate material should possess certain features. So there should be certain properties that the substrate material need to fulfill, and these properties are mentioned over here below. The first property is the substrate material that we are going to make use of should have a low cost, right? So unless and until the low cost substrate material is available, the entire costing of the fabrication expense is going to tend to increase. So the substrate material should be such that it should be easily available and it should be available at lower cost. Okay, it should be available in the suitable amount of thickness and permittivity values in order to be useful at the frequency range and achievable at the impedance values. So this is the second most important property of the substrate material. Okay, so we know that already the substrate thickness, how it is going to play an important role in the conduction of the microwave signal. Okay, we already know that if we make excessive more values of thickness of the substrate material, the spurious radiation may occur. So we need to have a precise control over controlling the thickness of the substrate material in order to avoid certain detrimental effects such as a spurious radiation. So the substrate material which we are going to make use in the circuit, it should be available in the variety of different thicknesses value. Okay, because this variable thickness availability of the substrate material is going to provide us helpfulness in order to achieve the impedance matching properties also. So this is an important property that the substrate material should possess. The third important property of the substrate material is they should have negligible dielectric loss. Now the dielectric loss of the substrate material we normally classify as a loss tangent. Okay, so the loss tangent of the dielectric material indicates the loss of the energy in the form of dissipation, right? So the loss that takes place with this substrate material, it should be as low as possible. The fourth important property, that the surface finishing must be good. Okay, so this is a required property in order to be utilized in microwave integrated circuit, and the finishing should range, the surface finishing should be of the order of 0.05 to 0.1 micron in order to keep low conductor loss with good metal film adhesion property. Okay, so if we are able to maintain the surface finishing or the roughness property of the substrate material, of the order of 0.05 to 0.1 micron. Okay, so this is a very low scale, right? If we are able to maintain the surface resistivity or the finishing type of roughness of the substrate material of this particular order, then it will guarantee us the low value of conductor loss, and it will also ensure good adhesion property with the metal film. Okay, and the fifth most important property that the substrate material should possess good mechanical strength, and they should possess thermal conductivity, and there should not be deformation of the substrate material during the high temperature operation of the microwave integrated circuit. So these are the main typical desired features of the substrate material which we normally need when it is utilized in the fabrication of microwave integrated circuit. Now here in the below table, we are going to list out some of the most commonly and popularly used substrate material in the manufacturing process of microwave integrated circuit. Okay, so these materials are alumina, sapphire, glass and gallium arsenide. Okay, so these materials are described for their property in terms of surface roughness. Okay, so the surface roughness is measured in terms of micron. Lesser is the surface roughness, better is the performance, right? We are going to have a very low loss tangent which is normally measured at the 10 gigahertz standard frequency range, and they should possess the value of loss tangent as low as possible, right? So the relative dielectric constant should be low. The thermal conductivity is mentioned in kilowatt per centimeter degree Celsius, and the dielectric strength should be high enough for this substrate material in order to withstand the breakdown voltages. Okay, and the typical application where these materials are used for the construction of the substrate, those are mentioned in the last column. For example, over here the alumina has the surface roughness in the range of 2 to 8. The loss tangent is less, it is in the range of 1 to 2. Relative dielectric constant is a medium value and it is up to 10. Thermal conductivity is 0.3 and dielectric strength is good, that is 4 kilovolt per centimeter. And typically the alumina is used as a substrate material for microstrip transmission lines, because the microstrip transmission line where they are getting supported with the alumina as a substrate material. Okay, so if we go to the other different types of a substrate materials like sapphire, glass and gallium arsenide, okay, so the surface roughness is even lesser than that. Okay, and however the loss tangent of the glass is biggest issue. Okay, and the best value of the thermal conductivity is being possessed by the gallium arsenide. Okay, so it is about 0.46 kilowatt per centimeter, and the dielectric strength, however, it is very low and it is just of the order of 0.35. And gallium arsenide material is used as a substrate during the fabrication of monolithic micro integrated circuit, and even they are used for the substrate material to construct microstrip transmission lines. Okay, so this is all about the different types of substrate material which we normally use in the fabrication process of the microwave integrated circuit. Now we go ahead and we will go and see the details of what different types of conductor materials we normally use for the fabrication of microwave integrated circuits, right? So again here the conductor material, whatever we are going to make use of, they should fulfill certain requirement or certain specification. These specifications are listed over here. The conductor material which we are going to make use, they should have a high value of conductivity. They should possess a high value of thermal coefficient of expansion. Okay, so the thermal coefficient of expansion means the changes in the dimension of the conductor as it is going to carry the thermal heat. Okay, we already know that whenever a conductor carries thermal heat, the dimension or the size of the conductor increases. Okay, this increase in the size of the conductor should be as less as possible when it is carrying a large amount of heat, and this particular property of conductor material is measured in terms of what we call it as a coefficient of thermal expansion. Okay, coefficient of thermal expansion. So this coefficient of thermal expansion should be as low as possible, which indicates that better thermal heat carrying capability of that particular conductor. Okay, if the thermal coefficient of expansion is large, it indicates that this particular conductor cannot withstand high values of thermal heat generated, and it will expand and it will change in size. Okay, so lower values of thermal coefficient of expansion for the given conductor material are always desirable. The third important property, that it should provide us a low resistance at especially at microwave operating frequency, right? Next property is they should have a good adhesive property so that they can be fastened over the substrate material. Okay, next one is they should provide us a good etchability and solderability property, because we know that by using conducting metal substances, metal objects, we can etch out and we can solder the material easily. Okay, and this can be done only with the help of good type of a conductors. They should possess easy depositing and electroplating properties. Okay, so these are also the desired properties of the different types of conductor material. Okay, now we are going to see some of the commonly used conductor material in the construction of microwave integrated circuit. Okay, and these are listed below over here, starting with the silver, copper, gold, chromium and tungsten, right? So the surface resistivity offered by silver is minimum when we compare with the other materials, right? So here we observe that the silver is going to offer us a best surface minimum resistivity, right? And similarly, the skin depth provided by the silver is among all other element is the best. Okay, but the thermal expansion coefficient, if we note down over here, that is a 21. Okay, so thermal expansion of coefficient is 21, and the adherence to the dielectric material is very poor. Okay, and the deposition technique when it is used with the silver material is mentioned, that is by evaporation technique we can deposit the silver material, right? Now next is a copper material. More or less the surface resistivity of copper and silver are similar. Okay, and here the thermal coefficient of expansion for the copper is lesser than that of the silver, right? Now here if we take use of the chromium material over here, if you see at the chromium material, the surface resistivity is a little bit higher. Okay, but here the adherence to the dielectric material is very good. Okay, and similarly if we compare the tungsten material as a metal, the dielectric adherence property is good among all of the others, so it is fairly high as far as the adherence property to the dielectric material is concerned. Tungsten material is going to perform best, right? On the other hand, if we compare in terms of surface resistivity offered by the metal, the silver is going to beat the other remaining metal types. Okay, so let us go ahead with the third type of material which we commonly used in the construction of microwave integrated circuit, and that is dielectric materials. Okay, so the dielectric materials used in the microwave integrated circuit are utilized as insulators. So please remember, this is a very important sentence. The dielectric materials are utilized as the insulators for making capacitors and making protective or insulating layers for active and passive devices. Okay, so this is the main use of utilizing the dielectric material in the construction of microwave integrated circuit. So what we observe from here, the dielectric materials are mainly used in order to act as an insulating material for constructing capacitors, and they are also used as a protective and insulating layer for active and passive devices. So this is the main use of dielectric material in the construction of microwave integrated circuit. And as usual, these dielectric material, they should again possess certain properties which makes them suitable to be utilized in fabrication of microwave integrated circuit. Okay, so what are these properties which are expected from the dielectric material? The properties which we normally expect that the dielectric material should provide to us is reproducibility. Okay, so reproducibility, what that indicates? It indicates that we should reproduce that particular dielectric material easily. Second, the dielectric material should possess a high value of breakdown voltage. We know the breakdown voltage, right? So they should be able to withstand high values of voltages which will get developed during the operation of microwave integrated circuit. The third property is similar to substrate material. The dielectric material should possess low value of dielectric loss tangent. Okay, and the fourth is they should have a property of good processability. Okay, they should have the property in order to perform the mechanical operation, in order to resize them, reshape them. All these properties are indicative of good processability, right? So the typical different types of dielectric material popularly used in the construction of microwave integrated circuit are listed below in this particular table. So the commonly used dielectric materials for microwave integrated circuits are silicon oxide, silicon dioxide, and silicon nitrate. Okay, so the deposition method is also mentioned over here, how these dielectric materials are implanted in the integrated circuit. So that indicates the deposition method. So the deposition of this dielectric material over the integrated circuit can be performed by evaporation process, by simple deposition process, or by making use of a sputtering. So let me explain you briefly what do we mean by these deposition technique. Deposition technique means integrating the dielectric material with the given microwave circuit in the construction. Okay, so this integration or addition of the dielectric material in the given microwave circuit can be done in a different ways. So the first way is a evaporation technique. So in the evaporation, the name itself indicates that whatever dielectric material you want to deposit, that will get evaporated first. Okay, and wherever we want to place this dielectric material, okay, so this dielectric material is evaporated, and over which the substrate material is held where the microwave integrated circuit is present. Okay, the second technique is a plain deposition technique. It is same process the way in which we used to perform the deposition technique in the integrated circuit. And the third technique of deposition is a new technique that we call it as a sputtering technique. Now actually in sputtering technique, what we do is, a sputtering is a special type of a deposition technique. So what we do in this particular deposition technique, we will make powder of the dielectric material. Okay, we make a powder of the dielectric material, and this powder of the dielectric material, wherever we want to deposit the dielectric material in the circuit, is implanted or it is fired with the help of gun mechanism. Okay, so there is a gun which fires the powder of the dielectric material wherever we want to deposit the dielectric material in the circuit. Okay, so for example, if this is a circuit, and over this circuit here, this is the position over which I want to deposit. So let us say this is a deposition area. Let us call this as a deposition area of dielectric, right? So how this can be done with the help of sputter type of deposition. In sputter type of a deposition, we take a dielectric material. Let us say this is a dielectric material. This dielectric material first converted into powder form. Okay, so it is converted into a powder form, and this powder is filled into a device called as a gun in this way. Okay, and this gun is then used to fire this powder over the surface where we want to deposit the dielectric material. Okay, and this particular process we call it as a sputter deposition techniques. Sputter deposition technique. So this is very simple to understand. What do we mean by sputtering process? Sputter deposition technique. So what is happening in sputter deposition technique? We take the dielectric material. Okay, so the dielectric material is present over here. We convert that dielectric material into powder, and this powder is fed to the gun device, and this gun is a special type of a gun which fires the powder at the given position in the circuit where we want to deposit the dielectric material. So this process we call it as a sputtering technique. Remember that in the sputtering technique, the powder fired by the gun ranges in the size of microns, and even it is in the form of atoms. So a very fine deposition of the dielectric material we will get with a sputtering technique, and this is a sophisticated technique of deposition method, right? So here some of the dielectric materials with their properties are mentioned. What is the particular values of relative dielectric constant, their relative dielectric strength, and microwave quality factor. Okay, so as far as quality factor is concerned, the silicon dioxide has a very good amount of the quality factor provided by the material properties. Okay, so we go ahead and we will see the last type of material which is used in the construction of microwave integrated circuit, and those are different types of resistive films, right? So the name itself indicates what do we mean by a resistive film. Those are mainly utilized for the purpose to generate a specific value of a resistance in the circuit, and even resistive films are used to construct attenuator circuit in the microwave integrated circuit. The resistive film in the microwave integrated circuits are needed to fabricate the resistors and attenuator circuit. See here, I will highlight this. Where we use resistive films in microwave integrated circuit, we use resistive films in the microwave integrated circuit in order to fabricate different values of resistors and attenuator circuit in the integrated circuit. Again, the resistive films, whatever we are making use in the construction of microwave integrated circuit, they should possess certain essential properties. The essential properties of resistive films are they should possess good stability in the sense good thermal stability and electrical stability, right? So they should possess low temperature coefficient of resistance, right? They should have a resistivity value in the range of 10 ohm to 2 kilo ohms per square, right? The temperature coefficient of resistance of the resistive films, it indicates that change in the resistance value. So what is the temperature coefficient of resistance? It indicates the change in the resistance value offered by the film resistor under the excitation of temperature. Okay, and generally it is expressed in parts per million per degree Celsius, right? So the commonly used resistive films in the microwave integrated circuit fabrication are listed below in the table. Okay, so the temperature coefficient of resistance, what is this particular parameter? This parameter indicates change in the resistance value which is getting excited because of the thermal effect. Okay, so what we normally desire, what type of thermal expansion coefficient that these resistive films are going to possess? The thermal expansion should be as low as possible because they should not change the resistance value much with the change in the thermal properties. Okay, so lesser is the value of thermal expansion of resistance, better is the value or better is the material to be used as a resistive film. So here the typical examples of resistive films materials are chromium, nickel, chromium and tantalum. Okay, and the method of deposition of these resistive films are mentioned over here. Evaporation technique is being used by nickel, chromium and chromium, while sputtering technique of deposition is used for the tantalum type of resistive films. The resistivity offered is also mentioned in the third column. Okay, so the temperature coefficient of resistance, it should be as low as possible, and in all these cases the temperature coefficient of resistance is low. Okay, now here the tantalum is going to provide us a best stability in terms of thermal activity and electrical activity when it is compared with chromium and nickel chromium, right? So these all are the different types of material which are used in the construction of microwave integrated circuit. So we discussed very first material, that is a substrate material. Okay, and the substrate materials are basically utilized for the fabrication of active devices, right? Then we went over to the conductor materials, and the use of the conductor material is mainly to provide the conducting mechanism over the given integrated circuit in the form of printed circuit applications. The dielectric materials, they are normally utilized in order to form the insulators and capacitors, and they are also utilized as an insulating material for active and passive devices. And finally, the different types of resistive films are used to produce the amount of resistance and attenuation needed into the microwave integrated circuit. Okay, so in general, the microwave integrated circuit materials are classified into four major categories: substrate material, then conductor material, then dielectric material, and finally resistive films. Okay, and finally the specific example of hybrid microwave integrated circuits and monolithic microwave integrated circuits are mentioned over here. Okay, so the examples of hybrid microwave integrated circuit, a typical applications are mentioned here. So that is used in a 12-watt gallium arsenic field effect transistor amplifier, which is going to provide us a gain around 58 dB and which is operating in the frequency range of 3.7 to 4.2 gigahertz. So this particular amplifier circuit is constructed using hybrid microwave integrated circuit technology. The second example is 1 watt KU band amplifier, which typically provides a gain around 4.5 dB operating at 16 gigahertz, which is able to provide us the operational bandwidth around 400 megahertz. The third example of hybrid micro integrated circuit is the low noise amplifier, which provides a gain of a 20 dB operating in the frequency range of 3.7 to 4.2 gigahertz. And also the hybrid microwave integrated circuits are widely used in various types of satellite communication. They are used in phased array radar system and in electronics warfare applications and airborne application, right? And similarly, typical usages of monolithic microwave integrated circuit, they are used in the 40 gigahertz distributed amplifier, which can provide us a gain of 4 dB. They are also used in the X band balanced mixer with a conversion loss around 6.5 dB. And the monolithic microwave integrated circuit, the best example is C band receiver in avionics application. So this C band receiver in avionics application is constructed using MMIC technology. Okay, so these are the typical and specific example applications of hybrid monolithic hybrid and monolithic microwave integrated circuit. Okay, so I hope you understood the different types of material and their significance in the construction and manufacturing process of microwave integrated circuit, right? So today we discussed the four major categories of the material which are used in the construction of microwave integrated circuit, that is the substrate material, the conductor material, the dielectric material, and the resistive films. And towards the end, we saw a typical example of circuits which are constructed by making use of hybrid technique and monolithic microwave integrated circuit techniques, right? So in our next lecture, which is going to be more or less the last lecture, we will cover the last topic of the last module, that is chip mathematics, wherein we are going to elaborate you the different types of calculations involved in the calculation of chip size and chip number. And we are also going to see one of the important parameter, that is the throughput of this integrated circuit technology, which we normally call it as a yield of the process. Okay, so in our next and last lecture, we will conduct this lecture on chip mathematics of the last module. So here we will stop, and thank you very much.